So welcome back. And in this lecture, we're going to combine forces on cells with fields. And one of the most trivial ways to combine them is chemotaxis, where you have a field, a concentration field, or something else like a stiffness field, and the cells respond to these fields by movement, following the gradient or following the opposite direction of the gradient. And I will put the simulation online. We'll do the self-generated gradient where a cell consumes the nutrient in its place and moves to another place to find more nutrient. Okay, so chemotaxis is one of the responses of cells to fields in the environment, but they can also respond to other types of fields that are not concentration of molecules dissolved in medium. For example, uh, durotaxis is response to rigidity, so cells tend to move towards places where the substrate is more adhesive, more rigid, because it's easier to migrate. There is apoptotaxis, which is similar to chemotaxis, but instead of a solute, the molecules they are bound to the substrate. And there are other types of field guiding migration. Here are some cool videos. I hope they don't have music of chemotaxis. The one on the left, someone is pipetting a chemoattractant and the cells are moving towards it. And on the right cell, this is, I think this is Dictyostelium discoideum in both. This is pattern formation when you zoom out. So this is a petri dish. And in the macroscopic scale, you can see these patterns forming. Another cool video of a cell macrophage, in this case, pursuing a bacterium and pushing objects around. And we have a similar simulation to this, like a toy model in CompuCell, trying to reproduce this kind of behavior. So the simplest way you can model chemotaxis is by applying a force to the cell that is proportional to the gradient of the chemical field, to the gradient of the concentration. If you have a minus sign, it means the cell is moving down gradient. And if you have a positive sign, it means that the cell is moving up gradient, so towards increasing levels of the field. Lambda chemo is the strength of this force. And so the force is both proportional to a parameter you set and the derivative of the chemical field. So the stronger the gradient, the stronger the force. Which makes sense. You would expect that if the gradient is very small, the cell will have less response to the gradient. In CompuCell, there are different chemotaxis algorithms. They are relative to how they set up how the pixel copies happen. For example, they can copy from cell A to cell B, from cell B to cell A, depending on the gradient. So there are multiple different ways. We're not going to dive deep into how they are implemented in CompuCell. We're going to just use the simple one, and this is the one I'm going to explain now. So in the simple one, we have the concentration in the target pixel when a copy is being made, and in the source pixel. We take the difference in concentration between the two pixels, and we multiply by lambda chemotaxis, the parameter, the chemotaxis parameter. With a minus sign, that's the energy contribution of that copy. So in this example here, suppose the numbers are representing the chemical concentrations. Of course, only the concentrations at the boundary of the cells of the cell are important because copies cannot happen between pixels of the same cell. Copies can only happen at the boundary. So suppose these numbers represent concentrations. What would you say is the tendency of copy here? What would you say is the tendency of cell movement? To what direction? That's the question. Considering that lambda chemotaxis is a positive parameter. So to answer this question, you would think about you pick a random pixel, for example, this one, and then you pick a neighbor pixel, for example, this one, and then you are going to ask whether making this copy, making this pixel become this pixel, sorry, or making this pixel become this pixel, if this would increase or decrease the energy based on this formula. So what is this formula doing? You take the concentration at the target pixel. In this case, the target pixel is this one, it's 2, minus the concentration of the source pixel, minus 2. This is 0. So there is no energy contribution here. We are looking for a negative energy contribution. So just by looking around and looking at the differences in chemical concentration, what is the net movement of the cell in your opinion? Is the cell going to move up, down, left, or right? Let's try to convince each other of what is the movement of the cell here, just by looking at the formula. Let's pick, for example, this pixel here and this pixel here. And I'm gonna ask if this pixel wants to become this cell here, okay? And estimate the contribution by the chemotaxis energy. So the concentration in the target pixel, so 1, it's 1. I want 1 to become white, okay, a white pixel. Minus 0. This is positive, and then multiplied by a lambda, which is positive, and a minus sign. This means that the energy variation is negative, which means that this copy is favorable. So it is favorable to it is favorable to make this pixel here white. This is a favorable copy. Which means that this pixel tends to copy in this direction, this pixel tends to copy in this direction, in this direction, in this direction, which is my next slide. So this is the answer. These are the tendencies of copy, and I missed one. So this copy here is also possible. So the net movement of the cell, you could say, is a little bit like in the diagonal, pointing down and to the right. If our lambda chem was negative, then it would be in the other direction. In CompuCell3D, you will find your Chemotaxis plugin on XML. If you imported it from the wizard, so this is an important step, you import it from wizard, or you can import from CC3D Twedit snippets. So you go to CC3D ML, drop down menu, and you select Chemotaxis. It is going to give you the syntax for setting up Chemotaxis. In the Chemotaxis plugin, you have a ChemotactTowards. This is a condition that defines what are the pixels the cell is allowed to copy to. So for example, suppose I have a cell here and then there is another cell here of the same type, and there is another cell over here of a different type. Okay? And everywhere else is medium. We have medium everywhere else. If I say that the blue cell has chemotaxis towards red and the field is growing to the right, the cell will copy just towards the red cell, and these copies here will not happen. Or for example, if I set chemotaxis towards medium and the gradient is to the right, the cell will not move to the right at all because chemotaxis is just towards medium. Okay? So you can set conditions in terms of what are the cell types that your chemotaxing cell is allowed to move towards. Lambda again is the strength of the chemotaxis force. So the higher the lambda, the more visible, the more noticeable the effect is. Of course, you can set a lambda that is too low that you don't observe anything, or a lambda that is too high that it causes artifacts or makes your cell disappear. And finally, we have the type of cell that is chemotaxing here. So in this case, we have cell A with a strength of 500 chemotaxing towards cell B. You can take the chemotaxis plugin on XML by going to CC3D drop-down menu, plugins, and selecting chemotaxis. This is to introduce a chemotaxis plugin to a simulation that doesn't have it. And you can also control chemotaxis through Python, the same way as we were doing with secretion, where you can define interesting behaviors. For example, you can define chemotaxis that is conditional on something that is happening on the simulation. You can do that via Python. And to get the syntax for chemotaxis in Python, you go to your steppables, then you use the drop-down menu CC3D Python, chemotaxis, and you can set Lambda chemotaxis in Python. Either give chemotaxis to a cell or modify the chemotaxis lambda parameter. In this exercise, we are going to use plots for the first time. And to use plots, you also use the CC3D, to edit snippets, code snippets, which you find in CC3D Python menu, scientific plots, and then you find all the setups for the start function to set it up, to adding data points to the plots, and doing other things like saving, erasing. And finally, this is our exercise. So please take your simulation where you have a constant field, sorry, a constant gradient or a linear field. That simulation where we had the lattice like this, and then we had the field. Uh, oh my God, I don't remember the order of the colors anymore. I think it's green here. Remember the simulation we had like this, or you can also take the simulation from the drive folder, or just generate it from scratch. I have the instructions here on how to generate the constant gradient from scratch. So you take that simulation with the constant gradient. So basically you fix constant value on the x left and right boundaries. And you define an initial concentration that is linear and compatible with the the boundary values. And then you define a cell, you draw a cell somewhere. I think I'm telling you to build the cell on the right side. And then you initialize a chemotaxis plugin. Actually, I'm just asking you to reach the chemotaxis plugin window in the wizard and take a look at the options. In the chemotaxis plugin window, there are all sorts of options. We're going to set regular chemotaxis type. Um, the other two, saturation linear, if you are interested in knowing what they do, you can take a look at the manuals. They are not the focus of today's lecture and they will not be useful for the exercises today. The field name, so you have to define a field and you set the exact same name of the field here. And you set a lambda chemotaxis parameter. Finally, you select a cell type for ChemotactTowards, or you can also type medium here. I just want you to set ChemotactTowards medium. This is actually not needed if you do not set ChemotactTowards anything. It is going to ChemotactTowards everything. So even if you don't set any ChemotactTowards here, it works. You can either type medium and hit add entry, or you can select medium, click ChemotactTowards, and then add entry. This button, ChemotactTowards, just writes the name of the cell type for you. So you can just type it if you want. And the drop down, but because it has to be exactly the same name, the drop down offers you all the options if you don't remember your cell types. And then you click add entry, and then it should show on the table like this, the name of the field, the cell type, the lambda, the ChemotactTowards cell types. And then because we didn't select any saturation, our saturation coefficient is 0, and our type is regular. Now try running the simulation and make sure you are getting a cell on the right side, one single cell, traveling to the left towards the increasing values of the field. And I'm going to do the exercise myself. CC3D project, new CC3D project. 200 lattice dimension for X, 100 for Y. Here I'm going to add a cell type. I'm going to add a field. I'm going to add contact, volume flux, and chemotaxis. In the chemotaxis plugin, I'm going to select the field oxygen. The lambda is 500. And then ChemotactTowards medium and add entry. Next and finish. Now in my XML, I will first of all make sure I have just one cell on the right side. So I can create a cell from, for example, 155 to 160 and a 5 by 5 cell from 45 to 50 in the y-axis. I'm going to define my boundary conditions, so constant value for the x-axis, constant value 1 in the left side and 0 on the right side. 1 on the left, 0 on the right. And on the y-axis, I'm going to set periodic. We don't need secretion. We don't need diffusion, but we can have it. And we don't need, but we definitely don't need diffusion and decay for cells. And we don't need decay at all. And now I'm going to set up my initial concentration expression. So this will be 1 minus x divided by 200. So this is my simulation now. Let me visualize cell borders. Cell border color. Cell border color is white. No, 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 black. Cell border, cluster border. Maybe cluster border is overriding. Yeah. Okay, I see my cell now. It's on the right side. And it's moving to the left. Beautifully. Okay. So next step is plotting. What are we plotting here? The cell position. The cell position over time. The position of the center of mass. And this is how you set up a plot window. So here you can plot cell volume, cell pressure, center of mass of the cell. You can calculate something and plot something else. You can plot the number of cells doing something, the ratio, the fraction of cells doing something. You can plot anything you would like. So Python gives you all the permissions to do anything you want with your cells. Of course, sometimes you won't have the access to the lecture, or accessing the lecture is too boring. So if you are on Twedit, one of the things you can do is going to CC3D Python, and then you go to scientific plots. Sorry, yeah, scientific plots, and you have all the options here for setting up a window in the start function, for adding data points in the step. If you are on VS Code, you can also use these snippets, okay? Let me just show you how it looks like. So if you're here on VS Code and you have like your steppables class somewhere, here I have a steppable class called circular domain initializer on VS Code. I have my start function, which I can close like this, and I don't have my step function. Let me go down here. Here I have my start and my step. Okay. So in measurements, I have a start function and a step function. And if you use VS Code like me, and you want to import code snippets, for example, the plots, you can go to your step function here, and then you go to your CC3D snippets, and you have access to all Python snippets here. For example, if you scientific plots, here you have the same stuff we have on Twedit. So I can hit add data points, and it's going to give me the code to the scientific plots, okay? And these are example codes, okay? They are not the codes you need. They're not exactly in the format you need. You have to give the appropriate measurement you want to plot and the name of the plot windows. And you can get your CC3D snippets on VS Code by downloading the CC3D extension. So you would go to extensions, type here CompuCell3D, and here they are. So you just install it, and then when you are editing your file, it shows up in your file explorer in the bottom of the file explorer right here. But because now we are using Twedit, you can access via CC3D Python, and then here you have all the options you need. Next, we can, I will show you how to manipulate chemotaxis in Python. And you can do that easily by using the code snippets. Just an introduction to what this why this can be useful. So imagine you have an exponential field instead of a linear field. Okay. So in the current example here, the field is linear, so the linear chemotaxis works fine everywhere in the low concentrations and in the high concentrations. But usually in your simulations, fields will be exponential because there is a source, a constant source somewhere, and there is a decay everywhere, and the profile of the field will be exponential instead of linear. So, but in biology, cells do respond very well to even to exponential gradients, exponential fields. So to have that behavior, to have your cell behaving more or less similarly in all concentrations of the field, even if your field is an exponential shape, we use a different expression for chemotaxis energy, or which we can manipulate using by changing the lambda chemotaxis parameter. We can go from a instead of just setting up a parameter, we set the lambda chemotaxis and we divide it by the concentration of the field. And then this is how our energy contribution will look like if we do that. So if we constantly during the simulation ask the cell what is the concentration of the field and update the parameter, the lambda chemotaxis parameter by dividing it by the field concentration, your cell will respond to the field, even if it's an exponential field, in a similar way as it responds to a linear field. Okay? This is the syntax you use in Python. So, and you can use a similar syntax to access any parameter of the of the XML specification. So you grab the XML object, the XML specification object, you set a lambda value, and you can also set a log scale coefficient. If you are using logarithmic scaled chemotaxis, that's not our case. We are only going to use the set lambda function. So you have a new value of lambda you want to set, you use cd.setLambda. And then if you do that, your cell, even though it's in an exponential field, it's going to behave in a similar way as it was responding in the linear field. So I will demonstrate it to you now. Very slowly, step by step, how we set this up, okay? Setting up the plot. I will go to CC3D Python, scientific plots, and setup on start function. Notice that I am on the start function for the setup, okay? And I want to add just one plot window. And I'm going to call this POS, POS. And there are other specifications here, like you can set up the title. So this is position versus time, Monte Carlo step. Linear, it's fine. Cell position. And then the color, we can change the color to green. And the style to dots. The size of the dots to 5. Okay. Now in the step function, we want to, inside this loop, for cell in self-cell list, we want to add a data point to the plot. So we come here to CC3D Python, scientific plots, and add the data points. It's giving me two options. I just need one of them because I just have one plot window. And here I manipulate what plot I'm changing. So it has to be the same name as the plot I created. So if here is pos like this, in the add data point it has to be the same name. And as arguments I'm giving time, MCS, and I'm going to give the cell center of mass. So cell.com. Now I save and I run, and a plot will show up. Probably. Yeah, there we go. So this is the center of mass of the cell, and it is decreasing as the cell moves to the left. And it decreases roughly linearly, because no matter where the cell is, the gradient is the same to the left and same exact gradient value, magnitude. And the cell responds to the gradient always in the same fashion, the same intensity. So the cell goes to the left in an approximately linear way. Of course, CPM has fluctuations, so this is not exactly aligned, but it is roughly aligned. Now, if we add decay and the field is exponential, the cell will not move at all, because here the field will be too mild. The gradient will be too mild for the cell to respond. And over here will be too strong. It can even destroy the cell because the cell will respond to a gradient that is too high, too intense. So let me stop here. So how do I set up first an exponential field? What do I have to do to produce an exponential field profile? I could change the initial concentration expression, but that won't last long. Add the decay. Yeah, that is the correct answer. So if I add the decay, the field will be an exponential shape. So for example, let's try 10 to the minus, let's try 10 to the minus 4 and see what happens. Let's change the initial concentration expression as well. I think that's a good idea. So I'm going to add both the decay and the initial concentration expression. So let's set it to 10 to the minus 4 and give it a initial concentration expression that follows more or less that exponential. So it is the exponential of minus the square root of gamma, our 10 to the minus 4 parameter, divided by our d parameter, our diffusion parameter. And it's asking us to use 0.1 in the slide. Times x. So if I do that and run, I have an exponential field there. And the cell doesn't go to the left. Oh, I don't know. Maybe it is going to the left. Do I have logarithmic chemotaxis and I don't know? No, this is regular chemotaxis. So it is going to the left, but it seems that it's going to the left very, very slowly. So no, it's not going to the left, not reliably at least. So what can I do to fix this to make my cell respond appropriately to the gradient, even though it's an exponential gradient? I set a lambda chemotaxis that is lambda divided by a saturation coefficient plus a concentration, the concentration of the field. And I'm going to do that by changing the lambda parameter in the Python code. So how do I do this? I'm going to my steppables here. And I will first take go to CC3D Python chemotaxis. And I'm going to do by cell ID modify. And it's giving me syntax to first get the chemotaxis plugin of a cell, of a certain cell, and with a certain field name. So in this line, I need to say exactly the same field name, oxygen. And it's expecting an input cell, so I cannot just leave this hanging around here. It has to go inside my for loop. And the rest of the syntax is if cd, so this is basically checking if you have a chemotaxis plugin, otherwise it's going to crash. I also pass this inside the for cell loop. So this command is basically getting the value of the lambda, which is not what we want. We want to set the value of the lambda, and we are going to set it to the value to 500, which is our original lambda. But we are going to divide it by a saturation value, such as 0.01, plus the concentration of the field at the position of the cell. So now I'm going to set lambda to 500 divided by a certain concentration. How do we get to the concentration? We go to the CC3D Python snippets. Then we find the chemical field manipulation. And we get field value. So I got the syntax for retrieving the value of the field at a certain coordinate. And here I just specify the cell center of mass. Now I plug this value of the field concentration here in the set lambda. And I should be good to go. So let me run this now. So now, because I'm dividing by the field concentration, I expect that the very low concentration value will increase the response of the cell for low concentration values. So the cell will still go to the left. But of course, it depends on my saturation coefficient. So if I set a saturation coefficient that is too high, the cell is not going to respond properly to the field. I think the cell is just um, wiggling around. So I will change my saturation value to something even lower than this, like 10 to the minus 6, and see if I am getting the correct the expected result. So the next exercise is the coolest one, in my opinion. It's the self-generated gradient exercise. So this is even simpler than the lambda, the saturated the logarithmic chemotaxis update, because here you can just set your simulation with XML and have it recover a very cool behavior where the cell is, because it's consuming nutrient in its current position and doing chemotaxis up gradient, the cell is constantly moving, eating nutrient in the field, and leaving a trail of deficit nutrient behind. And so it avoids its own path. It tries to not it tries to avoid places it has been in the past, which is a very cool behavior. And it has persistent movement. So this is a good way to get persistent migration in CompuCell or in models in general, simulations in general. And you just need two things. One is you need some field value, some field concentration in the medium, and you need your cell to consume it and do chemotaxis uh, towards the gradient. And then this is the output you have. So your cell is consuming, it is wiggling, and it's traveling up gradient, and it leaves a trail of nutrient behind. So you can download this simulation from the drive folder, which is the easiest option. Or you can just set it up. This is way easier than the exercise we were doing before. So this is the exercise. You have one cell, one single cell. You have a field at a constant concentration greater than zero everywhere. You let your cells consume this chemical field locally by either setting a decay in the position of your cell or using the uptake function. It's easier by just setting a decay. And then you let your cells chemotax towards higher chemical concentrations. And the name of the simulation is self-generated gradient. Self-generated cluster migration. To set it up from your pre-existing simulation, you can disregard all these changes. They are not going to be useful. Although you can keep the plots. And in your XML, what you want to do is to set a periodic boundary condition for your field on both axes. You want to set an initial concentration expression of, for example, 1 everywhere. You want to disable global decay, and you want a decay for your cell type. And this can be quite a very high decay. It's not a problem. It can be high decay. But I will do, yeah, I'll do 0.01. And that's it. This is all you need. Let me see if this works. Yeah, there we go. This is the self-generated gradient simulation. The cell is eating nutrients. Let me open another window here so we can see the cell. And in this case, because I don't have periodic boundary condition on the y-axis or on the x-axis, it reaches the boundary and it stays there. It glues to the boundary because of the adhesion the adhesion um, the adhesion plugin. So, but I can set the boundaries to periodic by going to CC3DML, POTS, CPM configuration, and I hit replace, and it pops up this window here, and I can just set the settings, the boundary conditions to periodic, hit OK, it updates to me, so now I have periodic on X and Y, and when I run again, the cell will cross the border and reappear on the other one. It leaves a trail behind. Of course, this trail is dissipating because of the diffusion, but we can zero the diffusion if we zero the diffusion, the trail will sit still, will stay still, and we'll see the self-avoidance behavior. Like the cell tries to connect with, if the cell happens to find its own past trajectory, it avoids it and chooses another direction to go.